Hello everyone, my name is Mohammed Osama, a PhD student at Deakin University. I'm presenting the work of my co-authors and myself on detecting ambiguities in natural language requirements. The title for our paper is Score-Based Automatic Detection and Resolution of Syntactic Ambiguity in Natural Language Requirements. The problem we are addressing is the detection and resolution of ambiguity in natural language requirements. Our focus primarily is on providing an automated solution to the problem without enforcing specific templates or constraints on how the requirements can be written. As a background, there are four main types of ambiguities in natural language: lexical ambiguity, syntactic ambiguity, semantic ambiguity, and pragmatic ambiguity. Each of these types can be further divided into subtypes or groups. Our focus is on syntactic ambiguity, covering all of its three subtypes: attachment, coordination, and analytical ambiguities. We focused on this type of ambiguity because with the current NLP technologies available to us, we can provide an automated approach to detect and resolve these issues without reliance on human interaction, which is the primary goal of our approach. In literature, there are mainly two strategies or two approaches to tackle the problem. There are methods that try to prevent having ambiguities in the first place. They mainly rely on enforcing patterns or boilerplates, or using specific structures and vocabularies with the written requirements. And there are other approaches that focus on detecting and resolving the ambiguities. Our approach can be classified under the second strategy, where we try to detect and resolve the ambiguities without changing or forcing the user to write the requirements in a specific way or manner. The flow or architecture of our approach is to get the sentences of the requirements from an input SRS document. We feed the sentences one by one into the SBADR, or the score-based ambiguity detector and resolver, which is our proposed approach. And we come up, after detecting the ambiguities, with possible interpretations if the sentence is deemed to be ambiguous. These possible interpretations are then displayed and shown to the user, where they can select like the most likely or the most correct interpretation. If the sentence is non-ambiguous, our approach is able to produce one meaningful interpretation for the input sentence. The pipeline or the architecture of our approach is: when we get the requirement sentence, we extract the top k best parsing trees. We do this by applying tokenization on the input sentence to extract a list of words. Then we apply PS tagging and parsing trees to get the best n parsing trees for the sentence. We get the top scored parsing trees. We rely in this process on the Stanford Core NLP. So we feed the parsing trees, the top n ones, into a stage of 4 filtering pipelines. Our pipelines are 4 stages. In the first one, we eliminate the meaningless parsing trees. In the second one, we eliminate parse trees with redundant structures. In the third one, we eliminate repeated interpretations. And in the fourth one, we keep the parsing trees with the high score after sorting the parsing trees within a specific variance. In our testing, we found 10% to be like the most effective one. That's the difference between the score from the least scored allowed parsing tree and the top one. If more than one meaningful tree is obtained, we display them for the user. The user can select the most correct one. If the sentence is not ambiguous, our approach produces one meaningful interpretation. Two examples in this slide show on the left, we have an input sentence, a simple one. I saw a boy. The only possible or correct interpretation for the sentence is displayed. 10 possible parsing trees are shown along with their scores, and each process responsible for eliminating some of these parsing trees. On the right, we can see a more complex version of the sentence where the system is able to produce to us the 5 possible interpretations after the rest have been eliminated. Another requirement example is shown where the system is also able to remove redundant or not needed interpretations for the input requirement and only keep the possible correct interpretations for the input requirement sentence. We evaluated the approach, our SBADR approach. We obtained a data set from an existing approach tackling the 3 main types of syntactic ambiguity, the Ambigo dataset, and we ran our approach on this dataset. We also evaluated in the first graph, we have the possible interpretations count per sentence. So it's like the percentage of sentences for each number of interpretation our system produces. And the second graph, it shows the percentage of correct interpretations for each interpretation count. We also tested our approach on more complex scenarios, and we are showing that our approach is also able to handle and cope with more complex situations of syntactic ambiguity. We compared the recall precision and F measure of our approach against the Ambigo tool, and we have presented the results for the 3 types of coordination, attachment, and analytical ambiguity. Thank you so much and hope you enjoyed the presentation.